fantastic statistician. He's been interested in a number of things, a lot of time series and spatial and like highly correlated data, high dimensional kind of work is where he started. And now he's gotten into, in his applied research, he's become very interested in like oceanography, which you can imagine has both like temporal and like multiple different dimensions in space. And then also kinesiology. I'm not sure if I'm pronouncing that right, but like sort of like the biomechanics of bodies, in particular like sort of athletes, and also like thinking about like concussion disorders and that kind of stuff. And we've like sort of like, you'll see like we kind of came together. Basically the story for this is when I started trying to be a professor, basically immediately was like, everyone was like, so you do machine learning, right? And I was like, I went to like Jordan because he's like my smart friend. And I was like, I don't think I know what machine learning is. And he's like, I don't think I know what machine learning is. So we spent like a couple of years trying to figure out what we think machine learning is. And that's what we're going to try to talk to you, or what we're going to talk to you about today. And I think like, you know, importantly, also part of this story is like, even if you ask people who call themselves machine learners, I'm not sure if we've got a great definition of what's going on with machine learning. I just want you to pause as like a group and just think like, I asked you to say, like, what's the difference between machine learning and biostatistics? Like, I really think about it. Like, what's the difference? I think the biggest difference probably is that machine learning is pretty cool, right? And like, we're just not. But like, seriously, like, so like, what's up with machine learning? Again, I really believe that a lot of people don't have a firm, like tight definition of this. And so you get these like weird conversations where it's like, okay, so like, is lasso like a stats method or machine learning? Because it got this like cool, like variable selection going on. There's like, and maybe you have to use computers to like implement it, but like statisticians built it mostly. And like, I don't know where the dividing line is. The one that always gets us really frustrated is like machine learners definitely have started to claim logistic regression. Like we've been doing that for decades. Like that is the oldest, but like I will actually, at the end of today, you will see me basically claim that you can do logistic regression in a machine learning way. All right, so that's going to be like one of the takeaways here is like, I think that's really important is like, well, I'll say this in a second, but I think one of the things we're trying to answer today is that like, for most of us traditional statisticians, biostatisticians, machine learning feels different. When you hear people talk about even causal inference when they're coming in from machine learning, they just think about it different. It's really hard to pin down. But I don't know until we started doing this, like if I could have defined to you what it is. And so here's one of the takeaways. If you want to check out for the rest of the talk, totally fine. Here's the takeaway, okay? The difference is not about the algorithms themselves. So it's a little bit like, it's not right to ask, it's like a logical fallacy to say like, is logistic regression machine learning or not? What we should be thinking about is how are we reasoning about data? How are we using data to convince ourselves that this algorithm is like sort of performing correctly? All right, so that's the takeaway. It's like, it's the logic or how we're combining data and convincing ourselves that we know what's going on. So we go into a lot of detail in this paper. This just came out in the spring in the Journal of Observational Studies. Got some links here. We can share the slide deck so you can get to it. But this is, this goes into a lot more detail than what we're going to do today. So for this talk, I'm going to start off with 3 projects, like applied projects, and then we'll move into some more theory. The 3 projects are a randomized trial. Then I'm going to talk about a model, and then I'm going to go into some machine learning work. And so we'll talk about it kind of a high level, but they're just vibes, okay? Like the reason I'm telling you about these is so you can have something to say like, okay, this is a little bit more like this style, this is a little bit more like this style, so we have something to sort of refer back to. That's why we're talking about these 3 different studies. For the second part of the talk, we'll abstract from that and really try to do a better job of saying there are 3 distinct styles that we think are out there for how you reason using data. The old school one, sort of the very foundation, is warranted reasoning. And that's like randomized trials and sampling. And that's distinct from when we build models and the structure of like how we use data and how they interact with our thinking there. And by the way, like since this is a causal inference group, this is where we spend a lot of our time. Like sort of the wars and stuff like that happen a lot of times in causal inference is between like folks who are a little bit more on the warranted reasoning side and some on the model reasoning side. But even like some of my favorite papers are like Liz Stewart's like non-parametric pre-processing, and Michael's got a nice paper about how you can combine models with like randomization, and so like you can hybridize these, okay? And I'm going to talk about warranted reasoning and model reasoning. And I'm going to try to say something kind of interesting in through there. But most of you, if you've done causal inference for a while, will have heard it. This is the exciting one. Okay. I'm going to hand it over the talk when we get to there to Jordan to introduce this third style of reasoning, which is really the core of machine learning. It's distinct. You've probably seen it before, but we'll really try to unpack it. So these different style of reasoning, these different styles tell us where you should look in the empirical evidence to say, is this like a good study or not? Like we know how to evaluate like a randomized trial, and that's kind of different from how we would evaluate like a model. And I'll unpack that later on. Okay, cool. So let's talk about these studies. The first one uses warranted reasoning. It's a randomized trial. So starting back in 2013, I got involved with running randomized trials on sexual assault prevention in the settlements of Nairobi, Kenya. So this is one of the pictures I took in Makuru, which is, we call them settlements, sometimes pejoratively known as like slums. So these are really tough environments. You can see that like the buildings are like, partially made from mud and from, found materials. That's an open sewage pit, chickens running around. These are tough environments. And one of the settlements that's particularly tough for high school age girls, they self-report about 1 in 4 of them per year are raped. So this is a very tough environment. That's part of the reason that we started deploying this intervention in this area and evaluating it there. So for about 10 years now, we've been going into Kenya, talking with school administrators, getting the program into the facilities, and then we've run now 2 randomized trials. And I'll tell you a little bit about both of them today, but later on I'm going to talk in Liz's lab group in more detail about some of this. But this is me and my research partner, Clea Sarnquist, talking to some of the folks there. The intervention itself is a class of interventions known as empowerment self-defense. There's actually some great researchers here, Michelle Decker, who's doing research on this kind of intervention as well. And in this setting, the organization that implements, what they did is they went and they talked to about 100 women in the settlements who had been sexually assaulted, and they abstracted common patterns for those assaults. And then what we did is build scenarios around those. So we help these young girls like understand that these are the common patterns that people use when they start like, predating. And then we built skills for them to deal with it, both like socially, how do you deal with this? And then also physical skills. And I'm not going to be able to talk a lot about this intervention, but it's a very effective intervention. It's actually been shown through several randomized trials to be effective both here, in Kenya, but then also in the United States and in Canada. So this class of interventions, it's a major breakthrough. Like in the past 10 years, since about 2010, there's been a major breakthrough in sexual assault. There's actually 4 or 5 different types of interventions that have demonstrated that they can bring down the rates of rape. Before that, it was purely like a theoretical, and we've now started to move into the empirical. The girls themselves really love this. And so it's a very interesting, you give them like really good social skills about how to be heard, by adults and that kind of stuff. And then we teach them how to kick butt. We teach them a mix of Brazilian Jiu-Jitsu and Krav Maga. If you're interested, I've got a link down here that talks about the intervention more, and so you can read about it. But the key here is that we ran a randomized trial. It's a cluster randomized trial. We went into the communities and we basically flipped the coin. Right, we said, you're going to get the treatment, you're not. Or actually, it's a delayed treatment. So we'll teach you a year from now. And from that, we then, analyzed the data that came out of it. Because we randomized, we could do some really strong claims about causality. And we found a 50% reduction in rape. And like I said, this has actually been replicated in different countries and that kind of stuff. So that's the first study, a randomized trial, cluster randomized. We went into the world and we said, the stochastic process, the random thing that's happening, we're going to create that, and then we'll collect some data down the road. I'm going to contrast that with a model reasoning approach to data analytics. So this one, same part of the study same type of intervention, where when we looked at the data from the baseline from the randomized trial, we noticed that we would ask 10 questions that were kind of related to like sexual assault, like, have you been raped? And then maybe a couple of questions later, like, if you were raped, who assaulted you? And so most of the girls, it was very consistent. All the stuff pointed to yes, or all of it pointed to no. But there's a number of the people who responded who had ambiguous results. So no, I've never been sexually assaulted. When I was sexually assaulted, it was like mom's boyfriend or something like that. And so what do you do with that? How do you adjudicate that? And by the way, if you've done behavioral stuff, you know that humans are very complicated, right? This kind of pattern is not uncommon where you have these ambiguous answers. And so, some of that's because of the confusion of the question. There's some subtlety about like sexual assault and consent, especially when we're dealing with middle school and high school girls the way we were. But also like answering something that's very sensitive, that's tough, right? I mean, like emotionally getting it out of you, but also maybe there are consequences. If it is mom's boyfriend, and you say this, what are the downstream consequences? So it's unsurprising that we found that. And there is literature to sort of try to understand why there are these underreports typically. And so what we did when we were trying to figure out like, well, how do we adjudicate? We built a model. So we said like, we're going to use a logistic regression. We're going to say the unambiguous yeses and the unambiguous no's. What are these two groups? How do they look like in terms of the way they answered other questions? And then we try to say like, okay, the ambiguous answers, people give us ambiguous answers, are they closer to the yeses or closer to the no? And I just want, so we can talk about that study, and I've got the link here so you can check it out. But the important part here is you notice this is different than the randomized trial. I am hypothesizing that this model here is like a reasonable approximation of the way the girls are making the decision-making process. Because what I'm about to do is like do things like, since I'm going to publish this, right? This is from baseline data, and we haven't collected the end line data. What I'm doing is locking myself in. I'm going to agree that this is the way we're going to adjudicate. So I better get this right. I'm going to have to call my shots. So what we're doing is, we look at those beta coefficients and we think very carefully about like, does that match everything we know from the literature? But I didn't force the girls to think this way and use those coefficients when they're like answer, right? That's different than the randomized trial. The random process that existed there was created by the statistician. Cool. Third project, machine learning. So for about 2 years now, there's a team of us at Stanford, call ourselves the Human Trafficking Data Lab. We've been partnered with the federal prosecutors in Brazil. We're just now starting to talk about this. But we've been going after human trafficking, labor trafficking, slave camps in the Brazilian rainforest. And this is a real problem. So basically like these like operations set up sort of in the rainforest, and they start like, you're just strip mining. And first thing they do is they cut down the trees, and sometimes they'll turn this into like farmland, for cattle or for soy production. But a lot of times it's to basically help for strip mining, what they call it, like pig iron, like crude iron, that they'll then like process and sell on the market. In these camps, they basically trick young men who are like in tough social economic situations to move out to these jobs that are really far away from other folks. And then once you get them there, you're stuck. I mean, there are venomous snakes running around or slithering around, and like, and it's gonna be really hard for you to get out. Also, you're economically like disadvantaged. So there's a lot, like once they get out there, they just stop paying them. And they've got, like the management team there, like they've got guns, right? And so what are you gonna do? So there's a lot of exploited labor, and the federal prosecutors have been aware of this, but this is kind of a tough problem for the prosecutors because they can't find these camps very easily because like they're far away from communities. Maybe the smoke gives it away a little bit. Like some of the, like someone living nearby may like phone in like, hey, there's a bunch of smoke kind of thing. But what they do is they set up these ovens, these kilns, and when they chop down the trees, they process them into charcoal. And so these, again, if we could find them, it would be relatively easy to do stuff about, and we can find them. So basically, our team has been using convolutional neural nets, using super fancy, right? Like convolutional neural, deep neural net processors. So, but what we do is we basically are able to find these camps because charcoal does not look like the rest of the Amazon. It's got a very clear, like sort of dark thing to it. They're also, and don't tell the bad guys this, they're putting in straight lines, which is super easy for us. Nature doesn't do a ton of straight lines, so our algorithms love that. They can totally find it. And so when we spent about 2 years like being able to really quickly process this because we swoop out basically the entire Amazon. The Amazon is about a third of the size of the continental United States. We can do this in an afternoon and with high like ability to find these. and to give you a sense of like some of the wins that we are sort of getting from this is like, we're really integrated with the federal prosecutors, so we can pull all their old records and get like sensitive stuff. So like back in 2019, they raided this site, and they found 5 guys who had been like sort of trafficked and slave labor, confirmed. Oops. We pulled data from that period, and we found 2 other sites that were very close, and we assumed that they were also probably similarly, like either run by a similar operation or probably had slave labor going on. And getting our inspection teams out there, it's like a dozen people. Some of them are like sort of inspectors, some of them are security forces. So once you get them out of the field, it would have been really easy to go raid these sites and inspect them as well, right? So we think that that's like one way we're going to get wins, is just like the efficiency of this. We also, and this is like, I'm super proud of this, and I know this is like the silliest GIF you've probably ever seen, but when we find a site, we can walk back in time for 12 months, and we put that together and we send this to the federal prosecutors, and you can kind of see this image here. When they start to deforest, it goes away, right? Like you can, and so that helps them understand, is this an active site or is it dormant? And they're going to hit the ones, they're going to raid the ones that are active. So, and we can pull other things, like we can pull when we find a site, like the administrative records and that kind of stuff. So we send over, we process this stuff and we send it over as a package. This is very different than my typical like causal inference stuff, but I'm going to talk a little bit about that. But excitingly, and this is the stuff that just happened this summer, is we piloted this in the field. We went in, this is a picture I took the night before we led our raids. This is one of the guys who's on our team. His name's Luis, but he's also a federal prosecutor. And so he's briefing the teams. This is another federal prosecutor. These are the labor inspectors, telling them the sites that we're maybe gonna hit the next day. These are tough environments, so we go in with security forces. We didn't go kinetic, is the way they talk about it, but like, but they have had to go into shootouts and that kind of stuff. So it was a little tense. But we found a bunch of guys, and we were able to hit a bunch of sites much faster than they normally can because we had all the information. Like it's like basically a traveling salesman problem. If you've ever heard that one, like we basically used Google Maps to figure out how we could get all these sites really quickly. And so we hit a bunch of sites before they sort of were ready for us, and we found a bunch of guys. So we're very excited. But also, I didn't go into the world and randomize. I didn't even really propose a data generating function, but still I'm using data, like measurements from satellites to find something. How did we get there, right? Like, and I will tell you, I think of it as a black box. I don't diagnose the issues with the algorithms that we're using here in the same way. So this is a third distinct, this is like sort of like, we're starting to get like this new stuff like a machine learning. So those are the 3 projects. And I think like Jordan and I really, there are other ways to tell this story, but Jordan and I sort of think about probably the easiest way to see the differences between these kinds of styles of thinking is about like when they fail, how do you know they're failing, or how does someone criticize you and say maybe your project's not doing a good job? So let's talk about the sexual assault project. So after that first randomized trial that I told you about, we got some more funding from the British government. So we ran a replication trial, much larger, more rigorous, same environment. And this is the stuff I'm going to be talking about in Liz's lab in just a little bit. But we got the most null result I've ever seen. Just heartbreaking. And there's a bunch of consequences to this. There's a bunch of things. I'm not going to be able to tell you, I'm not going to tell you all the things, but if you come to Liz's lab, I keep plugging your side. Yeah. And we'll bring like leftover cookies and stuff. Yeah. So that was tough. And so what ended up happening is we basically gave our data to 2 other teams. One from the South African Medical Research Council, we gave them their data, our analysis, all of our code, gave it to another team from the London School of Hygiene and Tropical Medicine, and they both evaluated us. And again, I'll go into detail in the next talk, but like, I'll tell you that almost all of the debate was about, did we implement the randomized trial in the right way? Did the randomization go through? Were there interference problems, like causal interference problems? Were there measurement errors? But it was always about the data that we generated and how it was being generated. They didn't like give me a hassle about like the inference model. And why is that? Well, that's because in a randomized trial, the hardest part of the place that you look for the data challenges is in the stochastic process that we created, and in the randomization that we did it, like that's the table 1, the balance table. Does it look like you randomize in the right way? Is there like measurement error kind of stuff? So it's basically the felicity to the proposed randomization that you had, right? That's where you get the rigor from a randomized trial. And that's what people, when it might have failed, that's where they look. It's not like, hey, you should have run a Wilcoxon, or you should have run a t-test. That's not where the debate occurs. So yeah, we spent a lot of time sort of thinking about both the randomization and the sampling scheme and that kind of stuff. Let's contrast that with like the adjudication model, that second project. So again, we got that, we ran like a logit, we got those beta coefficients. For us, before we published, what did we do to sort of convince ourselves that like things were okay? Well, first thing we did is check the assumptions, sort of like, thinking about like the residuals and like sort of plots and, that kind of stuff. To see if those were failing, we would be less likely to commit to that model and say that it's reasonable. The other thing you do and what we did is we looked at those beta coefficients. Was it positive when we would guess it would be positive? Was it negative and if not, if it wasn't matching our prior experience with this in the literature, then we would be, we would probably think about like running a different model or those kinds of tweaks, right? And then the other thing to think about is like, if we had published it and then we got the end line and the adjudication model was just wrong, if someone's going to challenge us, it's totally okay for them logically to say, you hypothesized the wrong model, you should have fit this squared term here. And that's, if they can justify it from the theory or like from the model fit, like that's a reasonable critique. And I just want to point out, that's not exactly the way you fight a randomized trial, right? When you fight a randomized trial, it's like, I did this thing. Well, maybe you didn't, but like, like here, it's like, I hypothesized this. Well, I could have hypothesized that. And that's a key difference where the models are a propositional kind of thing. Let's talk about this one, because this is the new machine learning kind of stuff. So when we were passing over these different files, so we were saying, hey, here are 11 sites that we think might be, like where we should go on these raids. They did like bench investigators, desk investigations, the federal prosecutors, and they confirmed that 4 of them were active. 2 of them, they weren't quite sure, and maybe we should go investigate in the field. Oh, I'm sorry. And then the 5th one, then 5 of them were false positives. And what's going on with that false positive? Well, much like a toddler, this algorithm learns super fast, but it loves water and it loves telling us about water. It's just like obsessed with water. And so it like tells us about rivers and tells us about lakes, and we can't get it to stop. And I have no idea why it's doing that. But those are kind of like fails, right? And I can't tell you, oh, this beta coefficient, it's going to do this because of this beta coefficient. It's a black box to me. So we've got this like, so what do you do when you're dealing with like a machine learning? I can tell you that it seems to be working. I tell you the properties of the algorithm, when it seems to be hitting, when it's not. But if I got that 50% fail rate, what do I do? Well, I don't know, like, should I be changing models? I don't know. So what we end up doing, and this is like sort of across the board with machine learning, you add more data. We have more people hand labeling from satellite images where we're pretty sure that's a site, give them more like true negatives. We tinker with the weights. And then we also put a human in the loop. So now when we requisition high resolution satellite data as well, so you can like just get a better view of it. And this kind of thing is like, we're kind of guessing. We don't know the exact structure. We don't know how the model is linking its covariate variation to the outcome, how it maps. But we're still able to say that the algorithm is working. And that's a little bit weird. Like a model says, here's the variation in the covariate space. Here's how I'm going to use that, like linearly additivity, and I'm going to link it to map it to the outcome. Well, we don't have that, but we're still able to say that this algorithm is performing well. How did we do that? And Jordan and I are going to talk a little bit about that, like with the outcome reasoning. So before we get into that, let's talk about the old school ones, warranted reasoning. So Fisher, we're pulling this from Fisher. Other folks have called this warranted before. So Fisher referred to the randomization inside of RCTs as the warrant for inference. Basically, it's the permission, it's the permit that allows you to then do all the inference. If you randomize, you can now do logic, all the logic flows through from like a permutational t-test, a Fisher exact, like it is all the hard, like sort of math, like that machinery is given to you by doing that in the real world randomization. This is our strongest form of inference. This is why like FDA trials like need this. This is why we don't just do models. And that's because we can make it true by construction. I'm gonna bold that as like the by construction is a really powerful thing. If I go into the real world and I do a sampling scheme or I implement a randomization, the properties of the inference that's going to occur later are really, strong. And you see this in other parts of math. People will talk about this with geometry. Like that was the first one that humans sort of figured out that we could do this kind of thing with, where you can take ideas like, hey, I have ideas about a circle, and if I use a compass or a protractor, I can bring this into the real world, right? Or I can like measure a triangle and then bring that into my theoretical. And so you can move between there's that moment where you do a thing in the real world that like puts those two together. If you think about like getting better at drawing circles, then it's going to be more like the mathematical properties, right? And we do that with RCTs. The rigor of an RCT is like, I proposed a data generating function. I thought about, I'm going to do a block randomization. I'm going to block permutum. I'm going to do a match pair randomization. And if I implement that in the right way, then all the stuff logically that I'm going to do for my inference later follows. So when we do the RCT, the rigor of it is that how did you bring it in the world? You had these theoretical ideas. How closely is that approximate? And if you start pointing out things like, hey, you got measurement error or people dropped out, that's an attack on your warrant, on your ability to actually do the inference, because it wasn't like you thought it was. And just a small thing is like, I'm trying to like keep the folks who've been doing this forever like interested in this talk. I mean, if you think about it, that's sort of what that whole movement inside of econ, where they were basically finding pseudo warrants, right? Is like they moved away from models, and people got really excited. They gave out a Nobel Prize for it. So basically recapturing what statisticians have been doing forever. So kudos to them for figuring that out. Let's talk about model reasoning. So models are propositional. Already we're different, right? Like we hypothesize that there is some known data generating function that's going to give rise, and we're going to like do everything predicated on that. So if we suppose that model is true, then we can think very carefully. This is like one of the big wins of a model is that we can then usually do things like decompose the variation. I can attribute variation to this X1 and this X3 and that kind of stuff. And usually we don't get all the way to that with like just a standard randomized trial. So yeah, good old linear regression, but like or linear model, but you can think about like other kinds of models here too. When we start using them, we don't make the linear model true. What we do instead is we say it's well approximated, and we sort of hope it's true. And we also probably have, and that's like things like the linearity and the additivity. We've got this error term, and usually we tell each other like these fun stories about the random process there for that, and that gives us everything that we can do. And even though I'm sort of like making fun of models a little bit, because like that's the way I was trained. Oh my gosh, they are so good. Linear models just crush it. Like they're really useful. They give us really good insights, even though they're probably wrong. Probably not everything is linear, right? Like maybe it's locally linear, but like, come on, not everything's linear. And so they're just unreasonably effective, even though they're not connected to the world in the tight way that a randomized trial is. And when we start thinking about debating models, I've already shown you this, but just to say it again, is like, we as statisticians think very carefully about there are assumptions and then there are parameters that come out of it. And so when you have assumptions, the reason we train you about those and the reason we build all these checks is because that's one of the points I would like say like, hey, I don't know if this is true, but like if the data are compatible with, I don't find anything wrong in the residuals or I don't find anything that looks nonlinear, I'm more likely to believe the conclusions that come out of it. That's why we have you obsess about and learn about those and the checks of those. It helps us think about how much we're going to trust the inference. Similar with parameters, I've already done this before, but when we give you the interpretations of those, and the reason we want you to think about those is because then what we can do is then we can think about all the other research that's been done and think about is what the model fits, like, are these compatible with everything else I've known? Right. And that's like a really important part of the story is like it's not just this one study, there's all this other literature, all this other knowing, and usually the parameters are the point of connection there. So those are the two things that you kind of like the empirical checks in a model that we usually use to convince ourselves that we're doing something, not insane. And so like here, like just to give you examples, like maybe we're trying to predict daily calories consumed, X1 is height. Just given what you know, if we fit a negative beta one, like that'd be kind of weird, right? Like the taller you are, the less you can think of scenarios, but like it'd be a little bit concerning. You maybe would like check it out. And then it's also sort of, part of our training as statisticians is we think like the data are what they are. Let's think like through our Rolodex of different, do people know what a Rolodex is? Like let's think of like our taxonomy, our different kinds of models that we have and try to pick one that most closely aligns with how we think the data are going to behave. All that I just said was said so much faster by Box. It was like, all models are wrong, some are useful, right? He's saying everything is propositional when you're using a model. Not the same thing for a randomized trial or sampling, right? Because we make those true by construction. And then some are useful, right? So he basically said all that other stuff like very quickly. You should pull that out whenever you want to impress people. Models are vital, and I don't want to, I have a little bit of a bent where I really like warranted reasoning, and that's what I do a lot of my research on. But models are really important because they allow us to think very carefully about how the variation is mapping, but also they can just answer a whole bunch of other questions that like RCTs and sampling aren't set up to. So they really do, they can also go into places that other ones can't. I'm going to hand this over to Jordan to introduce you to the third style.
Okay, so we're going to talk about the third style of reasoning, which we call outcome reasoning. And again, just to go back, this is the paper that Mike was talking about earlier, where you can find a lot of this information in a lot more detail. So I'm going to first talk a little bit about the common task framework. So much of the rapid success that we've seen in machine learning over the past couple of decades has come from this common task framework. It's really the intellectual engine. It's what's enabled such rapid progress. And if you want to read more about it, one of the first introductions of the CTF to the statistics community was from David Donahoe's 50 Years of Data Science, and it's a good place to learn more about it. From kind of a modern, decent example of the common task framework, you could look at the Netflix Prize. I'm going to talk a little bit more about where it's relaxed the common task framework in a minute. And also Kaggle competitions sometimes look like a common task framework type challenge, but they're also quite relaxed. For details of the common task framework, we start with a curated data set. So we have a very static data set. And along with that data set, it's available to everybody. So you could, if you're going to partake in the challenge, you can have access to data. You don't have to go collect your own data. A task is explicitly given. So we want to take our covariates X and we want to make a prediction on some outcome Y. And a metric is given for how they're going to evaluate performance. Okay, so it could be mean squared error, whatever kind of metric you are interested in using, but it's an explicit metric that everyone in the common task framework is going to use for that particular challenge. And then there's a holdout data set that's used to evaluate performance. So once everyone's fit their code, their algorithm, and they're happy with it, they send it to they essentially run the held out data set on the algorithm and see how well it does. And then we have a leaderboard of the different algorithms and which ones did best according to this metric that we specified. And so the one that does best is the top algorithm, and we move forward from there. So the reason why the CTF is so fast is because it's incredibly low friction. There's no link to sampling. The data set is given to you, so you don't have to worry about where it came from. There's no data generating function. We're not asked to recover the actual data generating function. We're asked to make a model that works for prediction or an algorithm that works for prediction. We can directly observe the ground truth. Here are the Y values that you want to predict, and here are your predictions. So we can that's how we assess the algorithm, as we say, how well did we do? How well did our predictions approximate the Y values we want? And the relative performance, how does my algorithm compare to your algorithm? Well, that's done through this targeted metric, right? Mean squared error, whatever it is. So I don't have to worry about if my algorithm's capturing certain variation and your algorithm's not capturing this. Doesn't matter. I'm doing better at predicting than you are, or vice versa. That's what matters, right? So we don't have to get into aspects of the covariates themselves. And the really nice thing is the computer does a lot of work, right? We push our button and go do something else. This has really allowed us to leverage the computer and to leverage this idea of how evaluation is incredibly easy to just move a lot faster with a lot fewer restrictions. So an interesting place to look at the use of computers in data science. You can go to Tukey's Sunset Salvo or Bryman's Two Cultures. They talk a lot about it there. So the CTF, it's you're probably aware that this sort of culture that's developed has led to some wildly complex algorithms that we just cannot describe mathematically. They somehow we don't understand how they take the variation in the covariate space and use them to make predictions. Mike talked earlier, you have an algorithm that's identifying rivers and you have no idea how to fix it because we don't know why it's actually identifying rivers incorrectly. So these are, often referred to as black box algorithms because we just don't have that access to them. So the common task framework is broken. So in the initial common task framework, it was really formalized in the 1980s by DARPA, and they were interested in human language technologies. They were interested in making, faster progress in human language technologies. And so they created the first common task framework. And really it was the idea behind it was we have these engineering challenges that we have to overcome that are common to a wide variety of of human language technology problems. And if we could just overcome these really small engineering challenges, we'll be making progress in all of the different fields that are relevant to human language technologies. And every year what they did was they got together and they decided on a data set, they decided on the task, they carefully thought about the metric, and this just year by year slowly moved. They weren't trying to make rapid progress. They weren't trying to, in particular, deploy these at all. The deployment was decades away. Okay, all they were trying to do was make really incremental progress, but rapidly. Every year we can actually see progress because we're starting to do better and better on these metrics that we're using. So the problem, though, is that as we started coming closer and closer to deployment, the CTF got relaxed. And in fact, in 2010s, if you ask someone in machine learning if they know what the CTF is, chances are they have no idea. It's just a part of the culture. This is how I grew up doing it. This is how my mentor did it. This is how I do it. And also, it's the CTF, sort of the culture of the CTF wasn't as formalized. Back then, you had DARPA doing it. There was a held out test data set. I forget which organization had the held out data set, but it was a governmental organization, would not let anyone see it. Until the very end of the year when they actually ran the competition. Nowadays, with like Netflix Prize, one of the ways they relaxed is you could actually query that held out data set more than once. I think at one point they were doing daily, you were allowed to actually query the held out data set. That's a huge problem, right? Kaggle competition, same thing. We also can run our own little CTF at our computer. We have a data set. We want to build up a machine learning algorithm. We just try several. We have a held out data set. We take all our, the 3 or 4 algorithms we trained, test them on the held out data set, see which one works best. It's a very relaxed form of the CTF, but it's one that's frequently used today. So it's led to a lot of issues in terms of, machine learning algorithms not really working in the wild. They work great on the static data set. You move them to the wild and they seem to fail. And so there are people that are working on trying to patch the CTF. So a few years ago, Ali Rahimi came out and said machine learning is alchemy. That was a fairly splashy a statement that got a lot of comments. He really wanted to go back and start thinking more about the mathematical framework. You got folks in Fair AI working on trying to fix how we train these algorithms to remove a lot of the biases that are present in them. You have Cynthia Rudin working on high stakes machine learning. So we're trying to fix the problems that we're seeing these algorithms have in the real world by fixing how we're training the problems there. There's an alternative approach. The idea is we don't have to really confine ourselves to just trying to fix the CTF. A good analogy here is cars. We drive cars on the road. We do not typically drive them in lakes or the ocean, but it doesn't mean that we have to fix cars. Cars are designed to be driven on the road. It just means that we shouldn't be driving cars in environments they're not meant for. We have boats for that. So it's the same idea. We don't necessarily have to fix the common task framework. We just have to know when we can actually use algorithms developed in that framework in the real world. And that's what Mike and I really try to do. There's another group actually at Princeton, Arvind Narayan in his lab, that were working on a taxonomy of ML studies. They essentially looked at ML in the wild, and they tried to develop an idea of when algorithms were failing or succeeding, under what conditions were they failing or succeeding. We took a little bit of a different, by the way, they have a really nice website. It's a lot of fun to look through. They talk about different problems, different projects, and if they fail or succeed, sort of what are the characteristics of those. We took a little bit of a different approach. So what we did is we carefully studied the common task framework and tried to abstract out why is it working when it works really well? What makes us believe in algorithms that are developed in the common task framework? And we developed this idea that you've heard Mike mention, which is outcome reasoning. That really the way that they're reasoning about data inside this development framework, the common task framework, is using outcome reasoning. So then we started to understand this idea of outcome reasoning and abstract the assumptions behind outcome reasoning. We took those assumptions and tried to develop a framework in which we could think about when is it appropriate, when does the situation that we're in, the prediction tasks that we want to do in the real world, when does that match with the assumptions that need to be met when you're using outcome reasoning? So that's the framework that we developed. And again, it's laid out in a lot more detail in this article, so I encourage you to go take a look at it. But the framework we sort of loosely call the principled prediction problem ontology. I'm only saying that once, not 5 times fast. Yeah. But it's really a pain to say. So the idea is that we're going to look for 4 features in this problem ontology. In a prediction problem of interest. We're going to look for 4 features to decide if a black box algorithm or if outcome reasoning can be deployed or not. The features are measurement. So the idea here is, can we measure a function of the outcomes? So we make a prediction. Can we observe an outcome or some function of the outcome and decide if our prediction problem is actually, or our algorithm is actually working in the wild? This is not an outlandish thing to ask for. In fact, Google and Uber both recently came out, this is several years ago now, and said that if you're using machine learning, you actually have to be able to follow up with that algorithm in the wild and make sure that it's working in the wild. So this is not something that's crazy to ask of outcome reasoning.
Sorry.
Yeah.
I know another paper. We go through some examples where people deploy this and they can't actually measure the outcome. It seems like, how could you even do that? There are very real use cases where you've seen it published in literature.
Yeah. So the next one is adaptability. Can we, if we see that our algorithm is not working, can we update it on a useful timescale? The third one's resilience. Obviously, the way that we know an algorithm is not working is because we see it fail. That's how we reason in outcome reasoning. And so are we okay with that? Are we okay building up failures before we say, wait a minute, we need a new algorithm here? Okay. And the fourth one is agnosis. So do we have a high tolerance for disagreement with beliefs? Again, these are often black boxes. We don't know why they're making the decisions they're making. It may not be for the reasons that we would normally be making the decisions. Are we okay with that discrepancy? And this is probably where a lot of those fair AI folks tend to sit, is in this feature of agnosis. So we collectively refer to these as MARA for hopefully obvious reasons. But MARA depends on the stakeholder. So who's deciding if a problem actually maps onto these features well? It's a group of people who are acting on behalf of potentially other people, and those are stakeholders. They're primary stakeholders, the ones that are making the decision whether or not to deploy. There are secondary stakeholders, the ones who are going to be affected by the decision to deploy. And so the idea is that people get together and decide if, for the stakeholders that under consideration, if these 4 problem features are actually met. It turns out that whether or not the 4 features are met depends on who the stakeholders are. We can easily construct situations where for one set of stakeholders, you have all 4 features met, no problem. For a different set of stakeholders, actually, there's a lot of concern here for meeting the 4 features, right? And patients and hospitals is a great space to think about that. And so it depends on who the stakeholders are. So with outcome reasoning, with MARA rather, there are 2 types of reasoning that we're going to contrast. There's, like I said, outcome reasoning. If the stakeholders agree that the problems satisfy the 4 MARA problem features, then we can deploy the algorithm, okay, successfully. And we can debate if it's working or not by watching its behavior in the real world, right? That's what we've agreed to as a stakeholder group, that if we satisfy all those 4 features, then we can use black box, and we're going to debate if it's working by looking at its actual performance. Okay, and we're going to make decisions. Should we pull the algorithm? Should we not? Should we keep deploying it based on, is it working in the wild? If we fail to satisfy any of those problem features, then we need a model or algorithm that can be reasoned about independently of the data used to fit the algorithm. Okay, so like the parameters. This allows us to debate prior to deploying the algorithm whether or not it's the model that Mike locked in, right? Prior to deploying this, is this a suitable model? We can get a consensus from scientists, from stakeholders. Do we think this model lines up or is appropriate for use for the prediction problem that we want to be using it in? So again, yeah, we have parameters with the model reasoning, but we can actually talk about specific parameters. Hey, this specific parameter violates my belief about the domain, and I don't think it's suitable for use moving forward, that kind of thing. So again, outcome reasoning rather happens after the deployment of an algorithm. The stakeholders have to be comfortable bearing the consequences of its errors as it accumulates errors. So this is one of the key features of thinking about outcome reasoning and model reasoning, which is that we have to assign accountability. And if we deploy an algorithm and it starts to fail, people come back to us and say, why did this fail? Are we okay with saying, we don't really know, it's the best we could do, what do you want us to do? If we're not okay with that in certain situations, we have to be able to say, we had a whole suite of experts look at this and agree that this was the best way forward. So it's the best we could have done. We did all of our due diligence. It's the best we could have done going forward. And so it's, any model is going to fail. Any approach is going to fail. It's the real world. And so we have to, by choosing either outcome reasoning or model reasoning for a prediction problem, we're choosing the way we're defending our choices when we actually go deploy an algorithm. So just a visualization here. Here's deployment. Model reasoning happens prior to deployment. We debate and defend our model prior to deploying the actual model itself. Outcome reasoning happens after deployment. And you could take a hybrid approach. Mike talked about hybrid approaches earlier. You can take a hybrid approach, debate a model prior, and then see how it performs after you deploy it. That's totally fine. But especially if you're using outcome reasoning alone, like with a black box algorithm, all of the reasoning about the performance of the algorithm in the wild is going to happen after you actually deploy it. This is distinct from building pipelines, right? So actually training and fitting the algorithm, that comes first. Then with model reasoning, we abstract the model, we look at it, we debate its parameters, et cetera, then we deploy. With outcome reasoning, we deploy, and then we look and see how it's performing. But prior to all of that, that's when you decide if you can use outcome reasoning or if you have to use model reasoning, right?
Yeah, one small thing I want to underline that Jordan's saying is outcome reasoning is moving at saying this is currently working, but it doesn't like abstracting it out and say like here are the conditions under which it would work the way a model does. So it's really a nice engineering like sort of definition of like it is like I can monitor it and I can see it, I can maybe like control it a little bit, but it has it's a very different problem, right? I can say it's currently working. That's like sort of the limit of algorithms, but it doesn't make it appeal to the
Yeah, and so the one thing I'll point out about deciding on an approach is it takes place prior to the pipeline building, and in particular, it's not technical. There's no appeal to technical. We're going to run cross-validation for this. We're going to, do this for a model reasoning or whatever. There's no technical parts of this. This is, does the problem itself lend itself to outcome reasoning or model reasoning? So anybody can understand this. Folks on Capitol Hill can understand this. Your collaborators, your non-technical collaborators can understand this. You can have discussions with them about whether or not, outcome reasoning is appropriate or whether you have to use model reasoning in a certain situation. Some final thoughts. Really, the difference between ML and biostats, as Mike alluded, or statistics, as Mike alluded to earlier, isn't the algorithms themselves. It's how we reason about those the data that we're using. Are we using outcome reasoning? Are we using model reasoning? And so, everyone in the data sciences, we conjecture really uses all three forms of reasoning, but in just different proportions. And so there's a dichotomy right now that Mike talked about. Is this ML, is this statistics? Really, that's the wrong great way to dichotomize. We should really be dichotomizing about, is this outcome reasoning, is this model reasoning, is this warranted reasoning? That's why something like the logistic regression can be both model and outcome reasoning. Are you primarily focused on the outcomes? How well is your logistic regression doing? Or are you focused on the parameters? What are the parameters saying about your domain of interest? Where is your reasoning about that particular model taking place? The reason why we're giving this talk today is we want more people like you thinking about outcome reasoning and its properties. We haven't finished the story yet. There are a lot of open questions. There are a lot of improvements to the framework that we're offering that can be made. We need a lot of folks thinking about this. We're also interested in linking up with folks in law and policy to think about how these will actually be used in practice when we're actually talking about setting policies with algorithms or models. How does this actually interplay with the real world in that sense? We also need to start teaching our students and collaborators about this third form of reasoning. We find that we did a brief survey of sort of student projects from around the country and took a look at what sorts of reasoning they were using on their capstone projects. We found an overwhelming majority of them were using outcome reasoning, and they didn't really even realize it, right? They just kind of went towards outcome reasoning because it's super easy. But often it was in circumstances where they probably shouldn't have been. And so we want students to understand, especially with the explosion of data science and data science programs, when is it appropriate to use these different forms of reasoning? Maybe you're really trained in outcome reasoning, you're from the machine learning community. Know when it's appropriate to punt the problem to a statistician, right? And not keep it in your domain, because it's the form of reasoning that you're most comfortable with isn't the form of reasoning that's required. At the very least, what we really need is a language for talking and teaching about outcome reasoning. And that's what Mara is doing. That's what we're trying to do with this talk, is to give you a language of going out and talking with your collaborators, with folks in government policy, whatever it is, about when these forms of reasoning are or are not appropriate. Okay, Mike's going to finish up with his favorite literary reference.
Okay, so I took a bunch of English classes when I was an undergrad, and you guys have to bear with it because I want to pay out on that. Thanks, Mom and Dad, for putting the bill. So one of my very favorite authors is Oscar Wilde, just super funny, really interesting. But he has this argument that's called the London fog argument. It comes from the decay of lying. So let me tell you about that, because I think it really I want you to understand how we feel about this. So turn of the century London, the Impressionists started drawing these really moody fogs, and it would capture the light and it would sort of make you feel something. And it really became the fog of London was a thing, and it became a very cultural touchstone, and it meant something. And I'm going to read through Oscar Wilde's argument about it, because he does something really weird. This is an argument that I did not buy at first, but basically he says, the only reason the London fog exists is because of artists. And I'm going to make a similar argument about statisticians in our role. Okay, so let me read you the argument. So, where, if not from the Impressionists, do we get those wonderful brown fogs that come creeping down our streets, blurring the gas lamps and changing the houses into monstrous shadows? To whom, if not to them and their master, do we owe the lovely silver mist that brood over our river and turn the faint forms of fading grace, curved bridges, and swaying barge? The extraordinary change that has taken place in the climate of London during the last 10 years is entirely due to a particular school of art. At present, people see fogs not because they are fogs, but because poets and painters have taught them the mysterious loveliness of such effects. There may have been fogs for centuries, I dare say there were, but no one saw them, and so we know nothing about them. They did not exist until art had invented them. And that's what I'm saying here is people have been using the common task framework. People have been using outcome reasoning. If you ask your machine learning buddies, they probably can't articulate it to. It's our job as statisticians and biostatisticians to articulate it, to make it kind of boring, write out the assumptions, get the mathematical properties in order for people to recognize that that's what's occurring, that they're using this different style. And then once we do that, we can start saying, here's where Jordan and I are trying to do this, and we're still struggling on exactly how to say this, but where are the boundaries of it? right? Like we try to give you that little taxonomy between like, we're, going back to model reasoning versus outcome reasoning, but we need to spend time. So we are going to be the poets. We are going to be the artists over the next 10 years. Like that's your job. We're old. We're going to retire. You guys need to figure out what are the mathematical properties. There's some Fisher running around in your generation who's going to write down the mathematical properties of outcome reasoning. And that's going to really help us articulate when is this safe, when is this done, and we'll start improving it, right? We get better versions of randomized trials by having all that. Cool. Thank you very much for listening to that. And if you guys want to talk more about this, we're around today and we're around tomorrow, but you can also email us as well. Great. Thank you, folks. If there are any questions, we got a couple more minutes. Go for it. Sorry, first. Oh.
So that the folks online can hear you.
Thank you for the interesting presentation. The 3 projects that Mike talked about got me thinking about the ethics of biostatistics. So I have 2 questions related to that.
Sure.
One is, how do you come up with the interventions you considered? For example, you talked about self-defense classes for the girls, but what about bystander interventor training?
Sure.
Or talking to men?
Yeah, sure.
And,
it's okay if I start with that one?
Yes.
So again, I apologize because this talk was not about all of those and I can go into more detail. So what we're talking about with the sexual assault prevention is a prevention program. And if you start thinking, I'm going to switch it, like, instead of like prevention, we often come up with the vaccine first, right? There's like, vaccination model. Then there's like, maybe you can go upstream and find like the vector that's carrying it. And then you can maybe like think about like some of the situational, there are different classes of interventions. And it turns out inside of sexual assault prevention, almost all of the models that are currently working and have been empirically demonstrated as working are the equivalent of vaccines. So what we know how to do right now is find people who are at high risk of being assaulted. So that tends to be women, men who have sex with men. And so the empowerment self-defense, it turns out that seems, and also sort of gender queer is another category that bears a lot of violence. And so the empowerment self-defense has been shown to be very effective there. Interestingly, the bystander intervention, there's a lot of good things it does. It does not prevent sexual assault. Over and over again, we run randomized trials on it. It can do other good things, but it doesn't prevent rape in the same level as something else. There's some really nice cognitive behavioral therapy programs. I'm blanking on a team. It's a team out of Hopkins that's also demonstrated for preventing sexual assault, particularly in like domestic abuse situations where the men and typically the men in the pairing are abusing drugs. They have a nice cognitive behavioral therapy intervention. Also, the other thing that I didn't really go into is starting about 2000, there were theories that were developed by sociologists, feminists, like who developed the idea of empowerment self-defense. For about 10 years, there was some like small piloting and that kind of stuff, but the theory of why it should be okay, both ethically and sort of like why it should function, that was all debated for about 10 years. And I only really jumped into the story in 2010 when we started to do it empirically. And then the last thing I think you mentioned is there are a couple different arguments about the ethics of treating people and giving them sort of a vaccine, the people who already have to carry the burden. Actually, I guess there are 3. One is we don't currently know how to identify and help mitigate people who perpetrate. There are a couple models. The most effective looks like maybe it's really hard to change in a preventive way people who are going to go on to assault. What we think might work, but it hasn't been demonstrated yet, is you teach people around them to not reinforce behaviors. And so that's the best model that we have geared towards like potential perpetrators. But the 2 arguments ethically for empowerment self-defense are utilitarian ethics. So it's like 50% reduction is pretty awesome. I mean, it's the only one that we know that's at 50%. The other one is deontological, which is like, turns out it's actually kind of fun. And we're actually giving a bunch of good skills. And so like they're deontological, particularly like arguments about why you might not. But the fact that we're transferring a bunch of portable skills that may have been demonstrated, we've got some preliminary evidence that shows like girls stay in school if we teach them this program. They also seem to be able to negotiate condom use. So there's a bunch of other sort of like cascading effects. Deontologically, we feel okay about it as well.
Okay, thank you. And then that was a really great response. I'm also wondering if you shared the results of your paper with the study participants and like what their reactions
Yeah.
were.
Yeah, so again, I'll talk a little bit more and keep plugging Liz's like lab, but like yes, so we use what's known as a community-based participatory model, CBPR, in a subdiscipline called citizen science models. So we spent a lot of time like in country talking with folks before. So you need to get buy-in from the schools. You also get buy-in from the community, so like parents and that kind of stuff. So we spent a lot of time upfront making sure that they understood what we were about to do. What's the treatment, what's the control, like that kind of stuff. And then we had a series of like, these are the results that we found afterwards, like readouts. And we also had commitments to, we all along the way, we were working with the Ministry of Education in Kenya to think about how they might scale it across the country. Yeah.
Thanks.
But I'll put in a plug. Community-based participatory research is an area that's mostly sort of like psych sociology. There could be like, I would say, okay, you guys are aware of it. Okay. I was going to put in a plug like, okay. Oh, that's fantastic. So it sounds like there's a lot available for folks who want to hear on community-based participatory research. And I'll put a little plug. They could benefit a lot from stats folks because they make a lot of claims that could be empirical that they're not currently making empirical. So I would just circle as like, if it's interesting to you, you know, Liz can probably plug you in better than I can, but like that would be a place where there'd be really interesting research for a statistician to do. I think there was, we're approaching time, but I think there was one more question. And I'll be around this afternoon. Jordan has to go teach. So he's going to disappear, but we're also around tomorrow in the morning. And, you know, I think we're going to maybe do some lunch. So if you have other questions. Yeah.
Hi, great talk. This is Leon, for those online who possibly can't see the room. My question about outcome is about outcome reasoning and whether, how you think about sort of classical statistical theory where around, for example, decision theory, where you just, you know, start out how you think about statistics as, you know, there's a task and there's a utility function and, you know, you do better or worse. And also, you know, like old theory about cross-validation, which is very similar to, you know, training, test, holdout, etc. Just a little bit of background, you know, I've had the experience of finding cross-validation pretty mysterious, and then you go back and, you know, read like the original AIC paper and so on. It's actually quite a lot clearer than the current wisdom. So what do you think about that old statistical theory and thinking? You know, do we need to go beyond that, or is there a case for sort of recovering some of it and bringing it into the pedagogy around machine learning and outcomes?
Sure. Jordan, do you want to also come up here for this? Okay, so I would probably start off by saying, like, yes, there are some clear connections. One thing that we didn't cover a lot, and this is not, I'm not exactly addressing your question, but I just want to point out that like algorithms or like models that we currently think of as purely machine learning or black box, they can change through time to be amenable to model reasoning. Like if you took like a deep neural net and you said, hey, there's a substructure. And like, even though it's doing all this fancy stuff, here's like a way to recover things that behave like parameters to it. Like now you can start reasoning about it using, you know, models and that kind of stuff. So some of the work, like when you propose, like, so just recently, it looks like Lasso, we now have a closed form solution for it. Right? Like that's kind of neat. Like it was just purely, I would say, being, you know, done through outcome reasoning. So you can see as time goes on, some of the algorithms and the ability to sort of make it meaningful statements in older traditional statistical thinking, it will migrate. But I do want to say that like outcome reasoning will probably stick around as a way, it's a very reasonable way to say, this is working right now. So it is a distinct, I don't think we'll ever, I don't want to get rid of it. But I think like you're pointing to something where like, yes, we could probably do a better job of describing its properties. But I'll hand that over to Jordan.
Yeah, so the I've actually had a bit of an identity crisis through all of this, mainly dealing with things like model selection, because in the, you know, to me, it's a very outcome reasoning based approach. And so yeah, so that's maybe a good example of hybrid. One of the things that Mike likes to talk about is that, you know, when we do model reasoning to some degree, I think you can look at the, you know, if you have a, say, a linear model that was chosen through cross-validation or through some sort of model selection, then you can talk about the model itself. I think where this breaks down is obviously when you start talking about you know, confidence on some of the parameters with this sort of post-selection inference. So this is maybe one area where Mike and I start to disagree a little bit on, and which is sort of probably going to become one of the future directions that he and I go into, is try and figure that that line out. I think there's an earlier line that, you know, people were earlier asking us about, which is like logistic regression. Where does that sit? That we've now come up with a really good answer to, which we mentioned in the talk. But the issues you're talking about with like with model selection and things like that are a little bit harder for me at least to think about where that line is.
Thanks.
Yeah.